Thank you very much for the kind invitation. I'm so excited to be here in Tromsø. It's such a wonderful and magic place. And today I'm going to tell you about a topic that I'm very excited about, which is discovering equations from data. Often nowadays, when we hear about AI for science, we often think about discovering molecules or discovering new drugs, or we think about AlphaFold. But what I hope to excite you, the machine learning community, is to discover insights and distill insights that could be very useful for humans, clinicians, but also many other areas, and discover new knowledge, and then apply this knowledge to build new science in medicine, but also beyond. What you'll hear today is research with a variety of my PhD students in Cambridge, my PhD students as well as my postdoc. First person is a postdoc, and you'll hear about some of their names as it goes. Before I jump into telling you the exact plan for today's lecture, let me say that I'm very excited about medicine. I didn't used to work always in medicine. It's relatively recent, well, recent by my age, not your age. So around 7 years ago, when I decided that I'm going to just focus on, as main application, I'm going to develop machine learning methods. So we are always trying not to apply existing methods, but trying to look at complex environments in medicine and distill from it insights. So this pushes us to build new machine learning models. So the focus is on new machine learning models that can be used in medicine, but also outside. And it's really a very interesting area because it provides a lot of new ideas. So it is often due to medicine and to discussions with clinicians that we come up with new ideas and new insights in machine learning. Today you are going to hear about discovery, but I want to tell you about other things I'm working on since we are here for a few days and maybe we have the opportunity to discuss not only about what I'm telling you in the keynote, but also other areas that I'm excited about and the group is working on. First, you see there in a green box, a box about data. And what we do in that particular box is two things. One is we are very involved with trying to use machine learning to improve the quality, the bias, the errors in the data. So we do quite a lot of work in the last 2 years on data-centric machine learning. So again, machine learning not to do analytics, but to improve the quality of the data. And this is actually a very, very exciting topic. Then another topic we are working on a lot is synthetic data. Can we build generative models of medical data from static to imaging to longitudinal data to high-dimensional data that can be exchanged among let's say, institutions. And this is very important in medicine, but is important in many other areas because often a clinical data set may not be possible to be shared with you due to privacy considerations. Synthetic data doesn't stop there. It is also useful for many other areas, such as, for instance, dealing with bias, dealing with changes from one domain or one country to another, etc., etc. If you are interested in synthetic data, we are running a AAAI tutorial, and it's going to be a hands-on tutorial, and we are going to release actually a very big open source package for generative models to generate synthetic data. So if you're interested in this particular topic of generating generative models, please stay in touch with us. Then we do a lot of work on analytics, from time series models to causal inference to causal effect inference, which is very useful for personalized therapeutics and personalized interventions, all the way to a new field that we try to kind of excite the community about, which is causal deep learning, which differs from causality in several important ways. I'll not talk about it here, but if you are interested, you can see more on our website. Then, in order for these analytics to be useful, we need to have interpretability and trustworthiness. These are two important pillars of the work that we are doing. So trying to build methods that are powerful and efficient, but also which are interpretable to humans. And the interpretability agenda has gone way beyond just feature interpretability. Nowadays, we have many, many different ways, from instance-based interpretability to generalization on concept-based interpretability to equations, which we'll see a very little bit in the beginning of the talk today, to the discussion on how we directly can discover interpretable models in complex settings, such as dynamical systems. Also, trustworthiness is important, so we try to know what we know and what we don't know, so a lot of work on uncertainty estimation. But maybe the most exciting part of our research, or at least the part that I'm most excited about, is this human-machine partnership. How can we really build machine learning models not to replace humans? I'm very concerned and kind of upset that a lot of the research agenda in deep learning is about creating superhuman intelligence, ignoring the role that the humans will need to play in the future in this area. And what we are trying to do is really to build machine learning that will support superhumans, but not supercomputers. So even in the agenda today, you will see quite a lot of focus on distilling knowledge, discovering knowledge to empower the human to be able to go forward and complete the scientific discovery process. As Robert has said, we are working quite a lot with clinicians, and this is an engagement session. I know that at least one clinician is in the room, so at least for that one clinician, there may be more. But we have an engagement session for clinicians that we started 2 years ago, where the focus is really to try to create a partnership and discuss with them to understand what are complex problems they want solved, and then go back to the drawing board and try to see if we can solve these problems and iterate with them. So if you are a clinician in the room, please join us. We have a next session on January the 18th at 4 p.m. UK time. But today the agenda is, I'm going to start by briefly telling you about why I'm excited about discovering equations from data. Very briefly, I will talk about how can we really deal with discovering explicit risk equations. But then I'm going to move to the main part of the talk today, which is discovering dynamical systems from data, which is really, really important because we don't want to look at static settings, but rather dynamic settings, which are important from medicine to finance to climate, but is also more complex. I'm then going to say that at times these discoveries, whether they are human discoveries or computer-made discoveries, lead to relatively simplistic equations and ordinal differential equations that may miss a lot of components, they may be misspecified, incomplete. So I'm going to, and maybe not personalized, and I'm going to talk about how we can maybe use machine learning to embed these expert equations into a larger set of variables and data to make more personalized and more precise predictions. And then I'm going to tell you a little bit about where we are going and hopefully have you join us. And you are going to see a few examples from cancer and COVID-19. So what I'm going to try to discover is what I call governing equations, which are these compact and closed form equations, which are really very simple expressions. I'm going to divide them in 4 different classes: explicit, implicit, ordinal differential equations, and partial differential equations. Most of the talk will be on the third box, the ODES. But if you look at me and say, hey, what she's talking about, I want to remind you about physics, because most of us have seen this type of governing equations in physics. And indeed, physics has made a very big impact in the discovery of these equations, most of the time by humans. So we all know, from the physics to the physiological to the psychological, brilliant Nobel Prize winners which discover such equations from data. However, this requires, if it is to only rely on such geniuses, we may need to wait a long time, and we really need to understand that this type of discoveries required a lot of insight, brilliance, domain knowledge, and they really discovered and teased equations from data. But we also need to remember that, first, not always we may have an Einstein or a Kahneman being born, but also the fact that at times humans may generate hypotheses that are wrong. Humanity believed for a very long time that the Earth is flat. We also know that at times in the human brain, it is difficult to consider many variables. We consider usually a few, but considering many is complex. And also quite complex is the fact that at times some of the variables may be really measured easily in the lab, but not in the real world, or vice versa. So at times in the lab, I may instrument something, I can observe, I can probe, I can understand, but these variables are very difficult to measure in the real world, which, and if you think about medicine, one thing is to do experiments in the lab, and something else is to do experiments in the hospital, in a place like the ICU, and vice versa. So we really need to have a way to bridge this discovery world in one domain to another. So what I'm trying really to propose is that we go beyond association, where we are now with machine learning, and we go even beyond causality. So we are all quite excited about causality. As a matter of fact, I'm co-organizing with two colleagues the CLEAR conference that's going to happen in Germany later this year in April. But while I'm very excited about causality, and in particular I'm interested in causal deep learning, which is an area that we are trying to really very much pioneer and grow, I'm even more excited to go one step further. And I'm going to put the discovery of equations that I'm going to discuss today at the highest level on this ladder, because it is not just discovering graphs. It is going to be discovering dynamical systems, how they evolve over time, and really come up with quantitative notions of the evolutions of such systems over time. So I'm going to describe dynamical systems through ordinal differential equations and beyond. So this is really important because often in medicine this is required. I think there is a problem.
Maybe a bit closer, maybe.
Oh, I'm sorry. Okay, I think I'm fine. I think I'm fine. It's
How is the audio?
not good. Oh, it's not good. Sometimes on, sometimes off. Hopefully.
Let me try this one, maybe.
Might be the cable. So I can try to change.
Maybe I try one more time, and I'm just very careful now. I think now it's okay, yes?
Yeah, it could be that it's
yeah,
so
thank you, thank you. Apologies for that. Okay, so what I'm going to try... No.
Let's try this one.
I think maybe the boxes are.
Maybe try to have the cable behind the back. Yeah, or over the shoulder, like that. Yeah, so.
Is it unmuted?
Oh, sorry, apologies. Thank you.
Let's try.
Thank you. Can you hear me? Can you hear me? It's either the audio or the slides. You can't have both. I'm just joking. Okay. So thank you so much. So the focus is really to try to discover equations from data. And the focus will be to use machine learning to generate hypotheses for the human, to empower the human to, with this type of insights. And I'm going to tell you how we would like to complete the cycle and keep the human in the loop at the very end. Okay. So we like such closed form equations because they are concise, transparent, interpretable to human experts, and also we can do a lot of analysis, inclusively equilibrium analysis. So I'm going to start by describing briefly about how we can discover from data explicit functions, but I'm going to stay here just in 2-3 slides and then move to the much more interesting journey of discovering dynamical systems from data. First, what should we think when we think risk equations? We can think, for instance, about regressions, And in particular, I'm going to put here an example from medicine. This is the NHS Predict risk prediction for breast cancer, for women that have already breast cancer, their survival given different types of characteristics. And of course, the clinical community likes such equations, they are used to them, and they are transparent. What about machine learning? Well, machine learning creates black boxes, and they are not equations. And unlike in other fields, in medicine, we need equations. For many domains, for instance, the Joint Committee on Cancer mandates having an equation associated with a black box. So something that we have done a few years back was to take a black box model of any kind and approximate it using symbolic metamodels. Metamodels are models of models. So we create a white box model, an explicit function model of the black box model. And we are doing that using, by learning symbolic expressions. And the way in which we are doing it, we can take, again, something from XGBoost to random forest to an ensemble method for static data, and we are talking here about static cross-sectional data, and I can turn it into an equation, and it could be, for instance, a polynomial, it can be an explicit function. I could also enlarge this class. I could be interested, for instance, in Bessel functions or more complex classes. But in medicine, often what we are interested in is to have something like regressions, but with nonlinear terms. So things like that are possible. We started in 2019, and then we continued the journey on trying to find, the way we are solving this problem is by finding good bases in which we can project these black box models and then find better and better approximations that approximate the black box model. Hence, we are able now to take something like XGBoost or deep learning models and approximate them using an explicit function, and then it is this explicit function that can be used to make predictions. However, as I mentioned, this is wonderful, it's good, so now there is no discussion of black box models for static cross-sectional data. We can turn them into these transparent explicit functions, but this is just useful for static data. And medicine, as my clinical collaborator, Earn McKinney, rightly says here, is a time series. What's interesting in medicine, and I will dare say in many other fields from climate to finance, is this evolution of the dynamical systems over time. So hence what we would like to do is we would like to learn from data governing equations, not in the form of regressions, but dynamical systems, so hence ordinal differential equations. And this is a much harder problem. The reason it's a much harder problem that has been unsolved for a very long time was because these differential equations involve derivatives, and they are commonly used to describe continuous dynamical systems, so they are exciting, but often they describe the change in the infinitesimal time, the time derivative. And for instance, in things like ordinal differential equations, which is one of the simplest incarnations of this, problems become very easily hard. So what we have done last year with my students Zhaoji and Christophe, we developed this methodology called DECODE, which was for the first time able to discover ordinal differential closed form, or I should be very careful here, important, closed form ordinal differential equations from data. Doing neural ODEs, which doesn't discover a closed form equation, is known, and I'm going to go back to that example later. But here I'm interested in really discovering something in the closed form that I can give to a human to inspect and do analysis on. So what's the problem? I'm having a trajectory of data. This is my data set. And what I'd like to discover from it is an ordinal differential equation, a system of ordinal differential equations. One more time, the reason this is challenging is because the time derivative is not observed in my data set. I only observe the states over time, and conventional symbolic regression methods are really not applicable. It is difficult to estimate the time derivative. I could do that, for instance, through a two-step symbolic regression, but as you are going to see a little bit later, usually these methods are known to fail. And the difficulty in solving this initial value problem of ODES is also there. So discovering really the initial condition is complex, and is complex in many scenarios, inclusively scenarios where the system may be chaotic, may have different types of characteristics that are complex to determine. And you will see even things that are not explicit, like neural ODEs, have very big problems and cannot learn effectively if more complex systems arise. And in medicine, this is very much the case. And last but not least, these are also computationally challenging. So what did we do in Decode? What was the unique insight? The unique insight was that we can characterize an ODE without referring to this derivative. So what we do is we piggyback on the variational formulation of ODEs, which says that we can define a functional, this functional C, which is now a function of two integrals. And what's interesting about these integrals is that they do not contain the derivative of x. What they do contain is the derivative of a function g, but g is something that you are going to see, I'm going to be able to construct, I'm going to be able to engineer. And I could design g's that are going to have easy to compute derivative. So through the variational formulation, I circumvented the complexity of dealing with derivatives in x into computing derivative in another function g. And again, we are using a lot of the variational formulation to build these algorithms. I'm not going to put you through a lot of complex math. Only thing I want to tell you is that we can use these insights to design our algorithms. So what you see here is this functional that we have, that we derive on the basis of the variational formulation, which tells us that solutions to our deep learning algorithm that is going to discover these equations from data is going to get better if this functional is going to be equal to 0 for all functions that are continually differentiable and vanishing at endpoints. And in fact, we are going to design a deep learning algorithm that is going to have a loss function that is going to minimize the value of this functional. And if we are able to do that, we are able to find closer and closer approximation to the true ODE that characterize the data set. Now, I'm not going to tell you about the mathematical derivations. They are in the paper. We were able to show mathematically that indeed, by defining the functionals in this way, you are able to discover closer and closer approximations. But the reason that I like this is that this doesn't provide only a theoretical justification of why we do that, but also a constructional one. Because it tells us that we can find functions g, we can construct function g that have a particular property. They need to fulfill this, what's shown in there in red. So we need to have functions g which form a Hilbert space, and again, are continually differentiable and are 0 at the endpoints. And one of the classes of functions, not the only one that does do that, is the sign basis. Now with this insight, we can now build a deep learning algorithm. We are starting with a data set, which is a set of observations of trajectories from healthcare or other domains. We are going to denoise and interpolate this data, and we are going to create these interpolated trajectories. And note that we are going to estimate trajectories and not derivatives. And what we are going to do now is we are going to solve an optimization that is going to discover the system of underlying ODEs that characterize the data Y. And what you see in this optimization is this functional that comes from the variational formulation. And we are going to use the testing functions that I just mentioned that are this basis representation. So now that we have this, we can solve a simple symbolic regression. And you may say, wait a minute, you just said that symbolic regression cannot be used here. Well, it cannot be used on the original data because there I will need to determine the derivatives. Here I don't. Here all I need to do is to determine this optimization, and I have g and I can compute easily the derivative of g, which is constructed. So now symbolic regression is a perfect okay tool to use because I circumvented this problem of solving the ODEs, the differential, the derivatives. Let me show to you what's possible now. I can start first with a system that I know. You'll say, wait a minute, what are you doing here? You told me that you can discover something new. Well, before I'm showing to you that I hopefully can discover something new, I want to show to you that I can discover something we know. So what I'm going to do is I'm going to take a class of systems and of dynamical systems, and I'm going to inject all sorts of perturbations. Noise, I'm going to remove samples, I'm going to do irregular sampling, I'm going to do all sorts of I'm going to give you more samples, less samples, and see if I can still unravel this underlying truth from which the data was generated. And I'm going to compare it against the only thing that's available, which is this two-step symbolic regression methods. I'm going to focus on asymmetric growth with saturation, partially because this is very popular and important in medicine, but you can use that for other examples. And in our paper, we have many other examples, mainly coming from physics, but we selected examples that really are underlying medical examples. And you see here the Gompertz and generalized logistic model. And what you see is that decode is indeed a lot better in terms of discovering the success probability. So success probability associated with having larger noise. The sampling rates are coarser and coarser, and we have fewer and fewer samples. Also, if we have something that's more chaotic or non-periodic, the story is even better. The reason it's even better is that decode not only does better than this symbolic regression, but also does better than things like neural ODEs. And don't forget, neural ODEs are not able to learn anything explicit and closed form, are just doing predictions. And yet neural ODEs have a very hard time with such systems because they need to solve the inverse value problem, and that's not possible. So even for prediction, forget about discovery, decode is a very powerful tool. Let's try to learn something we don't know. So ideally, I'd like to learn a new law. And what we try to do is we try to learn from clinical trials data on cancer patients that have been intervened on with chemotherapy, what is really the resulting outcome of these patients. And what you see here is one of the many representative traces. So we have quite a large number of patients. This is a clinical trial that was published by somebody else, and we used to do discovery from it. And what you can see is that the tumor growth of the patient after intervention goes down, and after some time they have a relapse. This is one of the examples. And what you see is for this exemplary setting is that decode is capable to keep this form, and also has a simpler equation than symbolic regression, which is more complex and is flat. Many more such examples are in our paper. Of course, ideally, we want to engage the scientific community to now use tools like decode and try to discover fundamental laws from data. And we can go one step further. We can even do something more complex, which is partial differential equations. But at this stage, you may wonder, did we completely solve the problem? Well, if it is to discover simple and powerful laws, yes, the answer is decode does a very good job. But the reality is that most of the expert models, whether it's physiology, pharmacology, discover such simple laws with few variables and relatively simple laws. And they are powerful. But there are still challenges. Often, there are many more variables that you would like to consider. You don't want to consider these simple laws with just few variables. You want to have a very high-dimensional data from which you are learning. And decode is not able to cope with that, like the human experts are not. Also, these models that decode or the human experts may discover may be incomplete, or may be incorrect, or may have variables that are only partially observable. So what we would like to do is we would like to embed this type of expert models, whether they are discovered by humans or by decode, into a larger equation such that we are able to make predictions at a personalized level based on more variables. And for that, we proposed a few years back a method for integrating expert ODEs, like the ones discovered by Decode, or which are known based on human knowledge, like for instance in pharmacology or physiology, into a neural ODE method to make predictions and to bridge the lab and the clinic. So this method, which we call latent hybridization model, it's exactly what the name says. I take an expert model coming from pharmacology or Decode, and I embed it into a system of neural ODEs, thereby hybridizing the two. What's interesting here is that while the expert model may contain only some variables, set of expert variables, selected by a human, and may be measurable in the lab. So in pharmacology, we often may measure certain things in the lab when creating the pharmacological model. Yet when this is given to the clinician in the clinic, many of these variables, for instance, such as different variables that relate to the immune response of the patient, are not measured. In addition, in many other settings, for instance, in Decode, I may learn from electronic health records data that may contain many variables, and Decode cannot cope with this very large number of variables. So often it is a human that may select a subset of variables of interest, and we may learn a simpler model, but then to the clinic, we may want a much more complex set of data to inform the predictions that are made. So the reason we would like to do that is, first, if we have this simpler model, the dynamical system, a closed-form dynamical system, the human can inspect it and can look at it, can look at stability regions, can understand it. It's a real equations. It also can provide us a link between these variables that the human wants to reason upon and what they see in the clinic and they can measure, which may differ, which may be larger set and maybe a different set. So what we would like to do is we would like to marry the two. We would like to marry what we can see in the real world, in the clinic, with what we can see in the lab. And provide, on one hand, interpretability with a simple equation, and yet predictability that's very high with a larger model. Also, this will be a fantastic inductive bias. We talk a lot in deep learning about inductive biases. We would like to learn from very few samples. So often in medicine, we don't have thousands and thousands. We may have hundreds of patients or 100 patients. So then deep learning is not a very effective tool. And this provides a way to introduce a dynamical system bias, an inductive bias, that can empower time series models in healthcare in the very low sample regime. So how do we do that? First, we have these latent variables that are learned by the machine learning model. So we are going to use the observational data in the clinic, in the real world, to learn the evolution of these unobserved latent variables. So we may learn some information about variables that are there and needed for the expert equation, but which we can't measure on the patient. We cannot break into the human body and measure certain things like we can in the lab. So we will need this model to infer them. Another thing that's interesting is that machine learning can create this bridge and can learn the relationship between what we can measure and expert variables, as well as other variables that maybe we don't even model with the expert equation. So what we will learn from data is unknown coefficients, all these gammas and thetas that you see over there, and we are estimating the initial condition of the patient. So we have often observations, but we don't know how the patient started. So we are able to infer that information from data, as well as how the variation, the initial states may reflect heterogeneity across the patients. So I don't want to have just like a case of Decode of pharmacological models, one equation per population. I want to have a personalized one to each one of you. So what we do is we learn with amortized variational inference, and the first step is an encoder network, which learns a variational distribution to approximate the posterior. Then in the second step, the decoder is computing the elbow, and we are sampling Z0 and numerically solve the ODE to really unravel Z of t. And then we are using for that a numerical ODE solver, an off-the-shelf solver to really solve this ODE. Then what we are doing on the basis of that, we are using the neural network G to map this latent space into the observational space. And we are able to make predictions about the patient going forward. And we are doing that based, again, on the latent variables as well as the inferred expert variables. So how do we do this training? As I mentioned, we are using this amortized variational inference, and we do end-to-end training using adjoint sensitivity gradient. Let me now take this to reality and to an example, but I'd like you to think about other examples that may be more familiar to you. The example I'm going to take is the large area of pharmacology. In medicine, the pharmacologists are some of the scientists that are empowering the clinical ecosystem, and they have many ordinal differential equations. And these ordinal differential equations are published. There is an entire vibrant literature of pharmacology, and often the clinicians may know about drugs that they want to use and the pharmacological model associated with them. But the trouble is that these pharmacological models often are using variables that cannot be measured by the doctor in the clinic. So this is a big problem. And we would like to use these models, these PKPD models. In the future, maybe Decode will discover and empower pharmacologists with new models. But now let's assume that these models may come from pharmacologists alone. And we are going to use the latent hybridization model to bridge the two. And the example I'm going to give is real. At the beginning of the pandemic, this drug called dexamethasone was first approved, first in the UK, but also in many other countries. And this story is about a collaboration I had not in the UK, but in the Netherlands, where the clinicians wanted to use dexamethasone, but they came to us with the following question. They said, well, it's wonderful we have dexamethasone, but this is used for something else usually. Now I need to use it to treat patients with COVID in the ICU. And what they discovered is that knowing the exact dose and how to intervene, so the interventions on this dynamical system, which is the human body with COVID, was very complex. Because for some patients, giving too much dose led to an autoimmune problem. For others, if there was too low, they may have secondary infections. So dosing it right for different individuals was complex. So they said, could you guys do something about it? And I said, okay, do you have tens of thousands of patients? And they said, what do you mean? This is COVID, we just have 100. So I said, oh my God, what are we going to do here? And that's when we discovered that we can use these inductive biases from medicine, from pharmacology, because dexamethasone is very well studied in the lab. So what we used is actually a pharmacological model for dexamethasone, and we used that to empower the machine learning model. So what we were able to do is this hybridization. So what you see is in the human body, what we can measure is the first panel. This is C-reactive protein. And what we would like to infer is what the expert variables in the lab are measuring or are based on, which is the immune response and the dexamethasone concentration, which are things I cannot measure in the patient. I measure this proxy, which is the C-reactive protein. So what the latent hybridization model did is that they took the C-reactive protein, which was measured in the patients, and inferred these other two variables that are only measured in the lab, use the pharmacological model to make predictions that the clinicians can then investigate, and they decided a dose to use on the basis of that. So what we did is we inferred these underlying models. Also, this was useful for prediction, because what you can see is we started with 100 patients in the Netherlands, and we went all the way to 1,000 patients. And models such as LSTMs, GRUs, and your favorite ensembles models in time series, deep learning models, were very ineffective. Here, what you see is the lower, the better, because we are talking about prediction in terms of mean square error. So what you see is that this latent hybridization model was much more effective when we have very few samples than the other models. So it's really not only interpretability that's there, but also you are able to learn more effectively if you like to make predictions. Now, are we done? We are still not done in some situations, because in medicine there are many types of differential equations. This is why medicine is such an interesting domain. we really may want to deal with delayed differential equations, integral differential equations, and there is really, we need a new way to capture the impact of history in these complex medical systems. I often say medicine is more complex than physics, but then I upset many of the physics students in my lab, so I need to be careful with that. It's complex in the sense that really we cannot do a lot of experiments in the human body and look inside in the way in which we are building better and better equipment to look at physics. So what do we really want to capture? We want to capture not only ODEs. ODEs are good for pharmacokinetic, pharmacodynamic models that are like the ones I described. But if we start to look at cardiac tissue, delayed peak-EPD models, epidemic models, forced oscillation in bioengineering, and more general healthcare analytics, we need a much more expressive class of ODEs. We need to go beyond, a much more specific class of differential equations that go beyond ODEs. So what we would like to do is we would like to have a way to capture that. Neural ODEs are not sufficient here. So what we did is, more recently, we built this neural Laplace. I will not tell you much about it, but I'm going to say that if you are interested in going beyond just neural ODEs, if in your environment where there is finance or medicine or climate, which are free environments where we really need to go beyond ODEs, then what I'd like to propose to you is to take a look at neural Laplace, which models a much broader class of differential equations than neural ODEs in the Laplace domain. And this does not require the user to specify the class of differential equations a priori, and it can learn implicitly. And it really performs a lot better than neural ODEs. And my student has some beautiful graphs, so even if you want to just play with some beautiful graphs, you can take a look at our website. With that being said, let me complete the story. So again, in the beginning of this talk, I talked about how can we empower humans, not replace humans, by discovering equations from data, which are then given as insight to the human, which can then distill new hypotheses, may collect new data, may do different experiments informed by this, and may create new equations in the form of structural knowledge, which then can be given back to us, the machine learners, to inject as inductive prior. So we are the computer people there. I'm the computer person there. So we get this new information now from the scientists in the form of the structural knowledge, which we can then inject as inductive biases in our deep learning method, such that we can learn more effectively, inclusively in the low sample regime, thereby achieving more interpretable, but also higher performance. We are not done. We need to develop a lot more tools in this type of framework. But hopefully this will provide you some food for thought, and hopefully you can join us. If you are interested in this agenda, we do have an engagement session, which I started together with my students, again, during the pandemic, but we are still ongoing, where we are meeting every month to discuss exciting ideas in machine learning. One of the last ones had the director of Google Brain, Isabelle Guillon, talking to us about data-centric machine learning. The next one is going to be on February the 1st at 4 p.m. UK time, and we are going to talk about synthetic data, and we are going to have 10 different people from the industry thinking with us about synthetic data. So if you are interested, please join us. We would like to create an online community that meets online in between these wonderful in-person conferences. Thank you very much.